Hi everyone, this is Ron Batum with Atlanta Functional Programming. Welcome to another episode of the Haskell Study Group. My apologies for starting late. I was having some technical difficulties trying to finalize some issues that I've had with do Emacs the last couple of weeks that I think I resolved for the most part in console mode. So we can actually get started here today with some more of a interactive demo than what we had last time, where we had to constantly reload our files as soon as we edited our Haskell buffer. Last time when we talked about Haskell, we discussed the topic of lists and gave kind of a brief overview of the list data structure, the syntactic sugar related to actually creating lists, and some examples such as defining functions on top of lists that leverages the pattern matching features that Haskell provides. Today we're going to be discussing transforms, filtering of lists, as well as zipping, and then we'll start introducing the concept of folds, which are basically reductions in Haskell. For folks who are coming in from other languages, think the reduce functionality that you may have encountered in your language of choice, since reduce is now becoming a very popular thing to be implemented. It's been around in many different forms in various programming languages over the years. For example, since C++98, it was available as did accumulate obviously in Common Lisp, but before that it was known as reduce too as well. It's available in OCaml as both. I think in OCaml it's actually fold left and fold right, which follows some of the same syntax that we'd be encountering in Haskell. But I am going a bit ahead, so let's talk about list transformations first. Last time we ended with this concept of non-strict evaluation and the spines. And this concept is a very important concept to be aware of when you are discussing Haskell itself, just because of the fact that it determines how a particular data structure or a particular evaluation would occur just based on the nature of the data that you're dealing with. You may recall that we introduced this concept that the Haskell book calls spine, which is, at least when dealing with consoles and lists, it becomes very important to actually see that, and that's because of the fact that with consoles, it's abundantly clear actually how the initial value or the first part of the list is connected to the rest of the list in this spinal structure, and it helps you actually, when you draw it out, to be able to see the particular place where the left side of the list is attached to the right side, which gives you an indication, at least when you are dealing with left to right applicativity of functions, which often is what most people are aware. A function when you're applying to a particular data structure starts at the leftmost element, the begin element, and goes until the end of the list. You could see how lazy evaluation can actually adopt this quote-unquote spine and this concept of the weak head normal form to actually go in and compute only what it needs to compute at the time that it's been demanded to compute those values. All right, this is what kind of gives Haskell some of its lazy structure and its lazy evaluation features. This concept is a very important thing to at least be aware of, just because of the fact that when we start talking about performance-sensitive code, there's some things that was introduced in this chapter, and it's going to be introduced in later on, that will become abundantly clear when you start writing code. Some of the performance issues that are going to be there. Specifically, there's this mantra that was in the list transformation section that I thought was a pretty neat thing to be aware of, which is non-strictness in the spine and strictness in the leaves. And this concept we'll be discussing as we go through list transformations. So what is available in list transformation? What are we talking about when we talk about list transformations? Well, you are aware that the list itself is a very recursive structure, and it starts with a single value in the list, and then you have this con structure that allows you to determine whether or not you can get the rest of the list. Has a pointer I'm using pointer in a very conceptual sense here, or you're making a recursive call. So it's basically some pointer in the structure to actually go and determine what the next value to be evaluated on is. We've already talked about several things accessing this. You may recall that we created the safe head and safe tail functions that takes in a list and actually returns kind of this maybe value that will determine whether or not we have the rest of the list or nothing in the case of the empty list. This sort of structure is used inside a very common use case where you take in a list and you want to apply a function on top of every element in the list. This is what we're talking about when we're talking about a transformation. You're basically creating a new list with all these new transformed values, not modifying the old list. And in Haskell, this is a very simple, very direct thing to do. It's a very common thing to do that they've created a function and a pattern to actually go and handle it. One thing to be aware of for folks who are just learning functional programming, and more importantly are learning functional programming in Haskell, this is not specific to Haskell, but it's specific to any language where you are functionally creating a new list from an old list. A lot of times you will end up writing code that looks very declarative. It's not in the traditional sense where you are imperatively function by function looping through every item in the list to actually go and transform it. Although behind the scenes at a lower level it may end up doing that. You can ignore that for the time being. What you're really doing at a high level is you're applying this list to this function to the set of the list. And there are two functions in Haskell that actually handle this, determining depending upon what you're trying to, what kind of structure you're handling. The common one when we're dealing with lists specifically is the map function. Okay, and so if we look at the map function, you'll see that the map function actually just basically takes in a function. All right, that's your transformation function. This again, for folks who are just joining us, as a quick review, this is our curried function syntax. What it's doing is it's a 2-argument function. The first argument is a function that you're going to apply to the list, and the second argument is going to be the actual list itself that you're going to be transforming. And when you're writing it in this form, you could think that the first argument is a function and will return you a function that takes in the list and creates the new transformed list based on what's passed in the transformation function. Now, Haskell actually has a additional function called Fmap that we will be encountering later on when we're talking about functors. But Fmap is defined in the type class functor, and it will end up doing sort of the same thing. So if we look at Fmap here, it basically is going to display the type class functor, where functor is the constraint that basically says that if the data structure has this Fmap function defined, it'll go ahead and it will apply it to apply the function that you passed into Fmap into and create a new function that will take a functor of A and return a functor of B. We're not going to be talking about functors. That's a topic that's going to be covered later on when we start covering functors, applicatives, and monads. I'm only briefly mentioning it here just because of the fact that, and I kind of disagreed with this kind of approach in the book, but I understand why it is brought up at this point. Functors are another way of transforming lists. Lists actually implement the functor type class for lists for Fmap. And I think behind the scenes, Fmap on lists actually end up at some point, I think, converting into essentially a map call. But those are implementation details. You should not really need to be worried about those when you're applying a functor to a list, okay? I am only mentioning it just so that if you're wondering how one might end up using it or implementing it, it is there, okay? So this, if you look at map and Fmap, they're very similar in their definitions. Their Fmap, if we actually put them side by side here, we could see that map basically takes in a function and then creates a list. Returns a list. Just one moment. Sorry about that. I'm just gonna put my phone outside here so we don't get any interruptions. Okay. All right. We return here in the list, whereas with Fmap we have this other one. I'm going to align this up just so you can see the difference here. Oops. No. Okay. And this also takes in a function A that returns a B. This is your transformation function. A and B may look like generic type variables here, but remember, this is generic enough, and it can handle the case where A equals B. So it handles both cases for you. And what this does is what Fmap does is, as I said, is it creates a functor of A and returns a functor of B. So this is essentially applying behind the scenes the function, the transformation function inside of a value, but instead of actually returning the actual value like what map does, it actually wraps that in this functor interface that's going to end up allowing you to compose additional functions to take in this functor interface. And again, when we talk about functors, this will become apparent as to why this becomes very useful. But for now, just know that what we're doing here is we are taking in some sort of data structure and applying a function to every element in that data structure. So what does this do then with if we pass in any sort of function? Like let's say that we have a partially applied function. Okay. If we do this and we call info on this, did I mess this up here? We have map plus 1. Okay, it didn't. I didn't even have to use info on this. If we actually apply partially a function here, obviously the arguments that are being passed into here will become abundantly apparent. And again, the Haskell machinery behind the scenes will end up creating a function that has the strict type constraints applied to it. In this case, since we're trying to use an increment function, or +1, we are requiring that at the very least what's passed in the list is a numeric type. So that's where that numeric type class gets kicked into the actual function signature. This actually is injected automatically by Haskell when it's generating this partial function that it could be assigned to a variable if you wanted to. So if you wanted to say increment list, just like we normally do, to say +1, now we could just go ahead and apply this to our standard lists, and it will go ahead and generate them. Now, there is something about this particular list syntax that I'm going to mention in a minute here, but just be aware that the lazy evaluation rules and non-strict evaluation rules that we've talked about last time do apply here. We could see this in many different forms. If we just apply, this directly, we'll end up having what we had before. If we apply, obviously, it doesn't matter what, how the function, a partially function application works, it will actually apply in the same way, especially when you're dealing with commutative operations such as addition. Obviously, in this case, this also applies to Fmap, what we're doing here. And again, when I said what I said earlier about Fmap on lists, Fmap is defined on lists, so we end up being able to use either syntax here to actually go ahead and generate our code here. And of course, here we can also pass in the identity. Okay, map ID. It's going to be the same thing, and you can see that the behavior of both of these is consistent. Okay. Now, whereas map obviously created this signature that we had before, when we apply fmap to the increment function that we had before, you'll get a very different function signature. And the reason for this is because of the fact that fmap, again, is a functor type class. So what it's going to be dealing with is only functors. We saw that in its function signature, all right, that f of a, f of b is important to be aware of, just because of the fact that what that's telling you is although it's a transformation function on some sort of data structure, at the end of the day, that data structure must adhere to the function type class, functor type class, before fmap can be applied on it. So this is a slight difference between what map is showing you, and again, this is related to the functor design pattern, I'm starting to call it now. It's kind of how you are leveraging this functor type class that's available for you in Haskell to actually go in and determine the semantics associated with it. And again, we'll talk about that when we cover functors. I know I'm mentioning functors quite a bit here already, but it is important to be aware that it is a fairly complex topic, and for the time being, you just need to be aware that if you want to use functors immediately, like fmap and so forth, be aware that there's this type class in it, there's a signature, and there are certain rules associated with it. But when we encounter that topic and delve into that topic, we'll go into more detail about it. The map syntax itself, as you may know and may have kind of guessed based on the notation, is generating something of the equivalent of the desugared syntax that we've already seen before. Like, how does the evaluation kind of work through this? It's kind of important to understand. And it's related to how it's been defined. So if we go into map again, and we see that this list interface, one way to actually implement it is kind of, and I think it's probably easier just to first define it this way and then go through the list. As you all know, when you're defining a map function like this, leveraging especially the syntax that's available for us by Haskell, we're going to be using pattern matching to actually go ahead and implement this. Now, if we're implementing, in this case, kind of the basic map function that's already available to us. We actually, in this case, our base case is going to be the case that we're going to be dealing with the empty list. Well, in the case of the empty list, we don't need to worry about the function. This is why we have this underscore. That's the syntax, if you recall, to ignore any sort of arguments that are being passed in there. Or in the case of our recursive case, we're going to take in my function f and our list, which has a value x and x's. And what we're going to do is we're going to apply f to x and then pass in my map and the rest of x's. So it'll keep recursively defining here. What this means then is if we actually end up loading this and we have the function available to us, remember, this is going to end up creating kind of the same sort of my map syntax that we had earlier, where it's going to go ahead and convert and do whatever machinery it needs to do to pass in these partially applied functions. But the important thing to note is that because of this recursive structure, remember, it's going to be using the same sort of desugaring syntax that we've been talking about before. So the way it's going to apply my map 1 plus 1, 2, 3, 4 is going to actually be the equivalent of my map 1 plus, our list syntax. So we do 1, colon, 2, colon, 3, colon, 4, and then our empty list. Okay? And recall, actually, load this again. Recall that the syntax, specifically the console syntax, it's going to be it's an infix operator that has infix R, not infix L. What that's telling you is where the associativity is going to happen, right? This is why this syntax is written this way. Basically, the car, the first of the list, is going to be here, and the parentheses are going to associate to the right. So our recursive structure goes top down here until we hit the empty list. So why is that important? Well, when you evaluate my map with this increment function in this example, okay, 1 plus, and then we do 1, 2, 3, 4, okay. Multiplication failed. Hold on. Let's do this. Okay. Okay, good. And here you can see that there is no signatures associated with this. Okay, so we can add a list of integers here, just for the sake of getting our compiler, our highlighter all worked out here, because when you're defining stuff in a buffer, you have to go and define the function, the type signature for the actual variable or function that you're dealing with. Now, when you're applying this here, what's going to happen is in this particular case, it's going to go and first evaluate 1, and then call the recursive structure for 2, 3, 4, and it may not actually evaluate that just yet. This is again related to the association, the non-strict evaluation piece that we've been talking about last week about this. So what ends up happening is that the syntactic sugar that you're creating this here in this call will end up ultimately calling my map on the structure and traversing through the structure automatically and generate the final list for you. The reason why this is important, this non-strict evaluation, this desugaring syntax, it's important because of the fact that we can show you an example where the only time that this breaks down is when you're dealing with, like, say, an infinite structure, and you're only, applying this to like a partially applied list. So one example here is if you say a list equals my map 1 plus, okay, and we'll call this the successor list, actually, for the lack of a better term here. Okay, and here, notice that since we've applied to it and we created an infinite data structure, we actually did not generate any new code for this particular piece. Remember, there was a feature in Haskell called sprint that we can see where how much something has been evaluated. And at this point, sprint tells us that we didn't actually evaluate anything from here. So let's, if we take 5 from the successor list here, and then we created the successor list for the first 5 elements, and then we call sprint on successor list, you'll see that it still hasn't actually gone and actually evaluated anything here because it's not a finite list, right? And it's not a finite list of strings. Actually, I should be creating something here. This is the wrong function that I should be using. Yeah, let's do this. Let's use instead let me see if I can do this. Or no, that's not going to work because of this. Okay. There isn't a specific evaluation that we can use to actually go in and look at the structure that's been evaluated for this. It looks like for integers specifically. But you could adopt kind of something similar for strings for integers somehow. And I will look into that to see if there's a way to actually introspect this evaluation as we define this. The point is at the end of the day, this sort of structure prevents us. This non-strict evaluation prevents us from actually, going off the deep end and handling every single value up front. All right. A good way of actually illustrating this with integers is with using something called the prelude undefined function. This is an exception that's available inside the prelude that you could go and use to actually go and leverage to spit out stuff to the prelude when you're loading stuff into the Haskell record. So if we accidentally pass in undefined to, say, a partially applied function, you're going to get an exception here. All right. So let's see what we could do here if we create a list. Okay, grad list called 1, 2, 3 undefined, and now this is from the Haskell book. Okay, this example. And I thought this was a pretty neat example that we can leverage here. Okay, so you can see that if we pass in, if we try to evaluate this list, it's going to go ahead and generate this prelude, this undefined exception, but it's still going to spit out the first two lists. The first two values of the list. And that's because of the fact that at this point it has not actually, at the point of traversing through the list, it has not yet hit this undefined value because it wasn't eagerly adopted, it's lazily adopted. And as a result, it could actually continue traversing through this list. What does that mean? That means then for a given list structure, if it has something like this undefined structure here, we could still pass in this into our mapping functions, and as long as we only grab that which we need, you won't get an exception thrown. Now I know this sounds like something that could be abused, but it is a good function, a good good thing to have, because it allows you to at least maintain your evaluation order and verify some of your results, and then handle some of the error cases accordingly, especially as you are iterating through and dealing with subsets of data potentially. So one way of looking at this is if we go ahead and do what we were doing before, you're going to see that 1, 2 are both incremented, and then in the case of the third element, since it's on an undefined exception, an exception is thrown. But if we actually go in and just say take 2 of my map of 1 plus the list, you'll see that the exception is not thrown. We'll actually successfully go in and apply a function to the sublist. Okay. So this take 2 and this ability to actually create these sublists in combination with the map function allows you to create these very and the non-strict evaluation. It allows you to create some pretty interesting data structures, and gives you some building blocks to create some interesting data structures and how you could traverse them, how you could transform them. Because strictness is not preceded from the outside in an eager, like what eager evaluated programming languages does. We can leverage this example and create kind of a common pattern, which we'll touch base on when we're dealing with data structures in Haskell, where you can actually create lazy evaluated code, but the actual core of the lazy evaluated code is a strictly evaluated function. So you have to apply the function in an eager fashion. And this goes back to what I was saying earlier: lazy in the spine, strict in the leaves. Basically, in the con cells, you can have laziness. The structure itself can be lazy, but within the actual leaves, the values, the application of a function to a value could be very strict. And that can actually help you write fairly performant code in Haskell. Although if you're doing your day-to-day work, more than likely you will not encounter this at all. Are there questions on this? As I said, Fmap kind of works the same way as map does. Okay, except Fmap, you don't have to worry about handling. Fmap is not only specifically applied to lists, but it can be used for other data structures, which we'll touch base when we're dealing with functors. But for the sake of example here, the stuff that we showed you earlier, the same thing can actually apply. It actually work if you use Fmap directly. Okay, so if you do this on bad list, you'll end up getting the same stuff. If you do this using map itself, you'll get some of the same stuff. Like we said, both map and Fmap allows you to work on other list types. So you could have, say, for example, 1, 2, 2, 3, 3, 4, and 4, 5, and it will go ahead and oops, I forgot to add my good old friend here. A comma, and you can apply this to map or Fmap. So if you do this and use Fmap instead of map, you'll get the same answer. And of course, you can actually work on partially applied functions. We've already seen this with the successor function. That's 1 plus. You could also use this also with partially applying a take when dealing with particularly large collections. So if you wanted to grab, for example, the first 3 elements out of maybe a list of lists, each of which having 100 elements, you can see that this is going to actually work. And this also, again, works with Fmap too as well. And, you know, it's not just partially applied functions. You could actually pass in full lambda expressions. Like in this case, we could use this as a filter to apply a particular transformation depending upon certain conditions. Like, you know, if we want to negate only when we're dealing with even numbers, okay? If x mod x2 equals 0, then minus x else x. And we can apply this to the first 10 integers. You can see that can negate this. And again, this can apply also to if we end up using Fmap, same thing applies. Right? For the time being, they are equivalent. You'll see the differences between Fmap and map later on. So just keep that in mind. Are there questions on map or transforming values? Very quickly, the stuff that we talked about in map can also be used with a function called filter. Now there isn't a f filter or anything like this. Just filtering from a list of values based on some sort of predicate is available inside Haskell. It's called filter. It takes in a predicate that takes in a value and returns a bool, of course. Takes in a list and then returns the appropriate list. Common example, we want to apply even. You can see that we have the even predicate on the list of numbers, and we get only the even numbers of this list. Okay. Obviously, we don't. This can handle partially applied functions. So, like if you are looking for, say, a string match, say equals, you know, some particular character, all right, and we pass in, you know, a string here. You can see that, you know, the subset of the string will filter out the B's and only return you the A's. You can use this also with an anonymous function, or so like let's say that you have on some list x's, okay, and then now we want to apply the filter on this whenever we are dealing with just to get the multiples of 3. All right, so as you know, you can either use modulus or you can use remainder. We're using remainder in this example, and you pass in the x's, and you'll get in, you know, the first all the multiples of 3 from 1 through 100. There's a lot of different things that you could end up leveraging. We've used list comprehensions before last week. You can also use list comprehensions to actually leverage to do this kind of thing. Like, for example, we've seen this example here. Let's say that you are trying to check if we're dealing with a vowel. Okay, and we have the word abracadabra. Okay, you'll see that we are dealing with A's. You can also do the same thing here if you do X, pass in abracadabra, and you pass in element X, you see that you're going to get the same result. The point is with list comprehensions and with filters, there are multiple ways of actually addressing your use case inside of Haskell. You may want to figure out in what case where a filter may be more appropriate than, say, a list comprehension. It might be the fact that you want to pass in the filter as a partially applied function, to some list, and you want to just create a set of lists. It doesn't necessarily have to be, a particular it could be just a simple filter even, and then now you can actually apply this very quickly, and you label your filters accordingly. It may be that you need that use case where you're partially applying and creating different filters, and then using that filters across different data sets. So you want to move the filters around. That's a design decision that you're going to have to make. In some cases, you may be just using one-off. So in that case, a list comprehension may be better. The point is that at the end of the day, Haskell does provide certain features for you in certain cases, depending upon if you need partial function application or you need something else. And knowing when to use what would make your designs much more clearer too as well. There's no single answer in a lot of cases when you're handling some of this. Another use case that we need to discuss is this concept of zipping lists. This is a very common use case from folks, especially folks coming in from Python, when they are coming into Haskell the first time. They're wondering if it's even if some of this exists, because Python has this zip operation that allows you to take in two lists and zip them together. What does that mean exactly? First, what that usually means is you are creating, given two lists, a new list that pairs up element by element the two lists up until the last list, the shorter list actually terminates. Okay, a good example is this. If they are the same size, if you have 1, 2, 3, 4, 5, 6, you are ending up getting a new list that has them paired up. Okay, if we look at the actual type signature of lists, zip, you'll see that zip takes two lists A and B and returns their pair, as you just saw illustrated here. The one thing that is not here that I think is important to recognize is these two lists don't necessarily have to be the same. size. All right. If they're not the same size as you can see here, the shorter list obviously is going to terminate the function evaluation. All right. This allows you to take in subsequent lists and then create, different types of zips. Okay, and this goes both ways. So if you have 1, 4, 5, you'll see that obviously the left hand side is gonna win here. Or if you have 1, 2, 3, and then 4, the right hand side is the right hand list is going to terminate first. At the end of the day, it's important to know that this particular thing is going to end up preventing any sort of potentially infinite recursion. So in this case, for example, you could pass in a list and a thing, and the empty list is going to actually go and terminate that, which is pretty useful. If you want to actually unzip a particular thing, you have an unzip function. Just like there's a zip, there's an unzip that you can leverage. So let's take, for example, the list. And first, I think it's important to first show you what unzip does. What unzip does is it takes a list of tuples, or a list of pairs in this case, and converts them into two separate lists. All right, and then it's returned as a tuple of two lists. To illustrate this, let's go ahead and take our example of 1, 2, 3, 4, 5, 6, which is going to generate our original list. Actually, let me go ahead and do this. Enter. If we unzip this guy, you'll end up getting the original list that we just created, but instead of getting them, has two separate multiple return values like you would in some languages like Lisp and Python, you'll end up getting them as a tuple, where the first argument is going to be the first element of each pair, and the second return value is going to be the second element of each pair. And of course, in this case, they're going to be they're the same type. You can certainly see if we end up doing, say, zip, unzip, $zip, A through B, 1 through 5. We'll end up getting a string on one type, and the rest of the other type is going to be a different type altogether. And this kind of way it works. Because zip has this feature of terminating on the shortest list, some information, depending upon the transformation pipeline, may be lost, right? So it is a lossy transformation. And again, this is because of the fact that we don't know, both sizes may not be the same when you pass into zip. So an example of this is let's take a look at the concept of SND, which will just take in our list of a tuple pair, and then return the second argument. If we pass in and want to get the second argument of some unzipped pair of a zip of let's say 1, 2, 1, 2, and 3, 4, 5, you'll see that since the zip transformation is going to terminate on the second argument, on the first argument's length, in this case it's 2, 5 is lost from this transformation. So it'll end up creating, a zip pair of 1, 3, and then 2, 4, and then unzip will create, a tuple where the first is 1, 2, which is our original left-hand side, and the second pair is going to be 3, 4, which 5 is lost. This means that, and this is very useful, important to know, this means that depending upon your transformation pipeline, you could use this as a filtering mechanism. Another thing to know about zipping lists is you could actually apply a function to the values of both lists in parallel. All right. So if you have 1, 2, 3, 4, and 4, 5, it may it can actually go in and apply this particular function to actually create a new list from these two lists. All right. So let's see how this might work. Okay. Let's say that you want to add each pair in a pair of lists. Okay. So let's say that we have the following list. We have 1, 2, 3, 10, 11. So let's say we do 1, 2, 3, 10 to 12. All right. So we have this list here. Okay. And let's say that we want to actually apply zip width, which zip width looks like the following signature. Right? Zip width is a transformation function that takes in a 2-argument function, curried of course, and returns a 3rd argument, and then it'll take in 2 lists, A and B, and then return the list. Okay. And what all this is doing is it's going to take each pair, unzip them, apply the function, and then add that to the final list. Okay, let's see how this looks. Let's take the simple addition function and apply it to 1, 2, 3, and 10 to 12. Well, this is going to apply 1 plus 10 gives us 11, 2 plus 11, which gives us 13, and 3 plus 12, which gives us 15. You can use this to actually generate different types of aggregations. You could also use it to do, say, like a simple Boolean math to check to see equality between two lists, like, for example, A through E and A through M. And you can see if they have some subset, if A through E and A through M are a subset, if one is a subset of another set, which is a pretty useful thing to do. In fact, you can use, I think there's a function called, that you can end up leveraging to actually apply a particular thing to make sure that all the predicates are the same. So in the same kind of context as well. Another final kind of like piece that I think is important to be aware of with zip width is you could also use it to quickly apply max between two values. So 10, 5, 34, 9, and 6, 8, 12, and 7. And you can see that will apply the appropriate thing to grab the maximum value of the two lists and put it in the final list. Okay. So that's a quick overview, finalizing our list. With the time permitting, I'm going to just briefly introduce folds, just to kind of introduce you to the subject, and we'll go and give this a more thorough treatment next time. But just briefly, coming in from other languages, you may have encountered the concept of of um, aggregating information from some sort of large data set into a much smaller, more concise form. All right, this is what we're talking about here. Okay, specifically, there is a concept that I'm just going to briefly mention here, and then we'll talk about it a little bit more detail next time. That folding introduces inside the Haskell space, and in general, when you're talking about folding in any other language, it introduces this concept. Although Haskell has this tries to use this lingo a little bit more, this terminology a little bit more consistently, a little bit more seriously. And that's the concept of a catamorphism. All right, a catamorphism is for folks who aren't familiar with the kind of where it's coming from. A catamorphism stems from the idea of category theory, and specifically, it means deconstructing. It's a function that deconstructs a data structure. Okay, so in the case of lists, if the console, which represents the spine, represents that structure, then the catamorphism, the fold, is what can reduce that structure. So it will take that structure and bring it down to its essence. All right, to its in the case of a list of a particular type, it's going to be the reduction of that is going to be whatever essentially represents that type. Okay, so and the transformation function that can take that type in and ultimately apply it in some way to do some sort of transformation into another type. Okay. Folds are a very, very important concept in just general computer science, because you do a lot more reductions in many different ways in many different use cases, and it becomes useful to understand what this folding does. I'm just going to quickly introduce you to the syntax that we will be looking at. One is two functions, and there are many different forms of this function, and the first one is fold R, which is fold right, and the other one is obviously fold L, which is fold left. Okay. Fold right and fold left are already available to you to actually go in and use. And I'm just going to close this session off with just introducing a very common use case that you would end up doing. You have some sort of collection of lists, and let's say that you're trying to apply a fold L on this, and let's say that we're going to apply a plus. A plus obviously takes in two arguments, a two-argument function, and then returns b, and it takes in an initial value, and let's say that we are going to pass in 1, 2, 5, and if we return it, you'll see that this is actually just doing a simple fold from the left, all right, and it's taking 0, adding 0 to 1, and then 1 to 2, and then it's going to essentially do 0 plus 1 plus 2 plus 3 plus 4 plus 5 from the right hand, from the left side, okay? That's what fold L does. Fold R is essentially the same concept. Again, if we do this with 0, 1 to 5, you'll see that you'll end up getting the same thing. But the difference is the location of where the reduction is starting. So in this case, it's not 0 plus 1 plus 2 plus 3 plus 4 plus 5. It's actually 1 plus 2. Actually, it's 0 plus 5 plus 4 plus 3 plus 2 plus 1. All right. And the reason is we're starting it from the right-hand side. We're actually going to go and, essentially apply it different, slightly differently here in this case. All right. And you can see this difference very quickly when you are applying, say, minus on, let's say we're using 0 again as our initial value, and we do 1, 2 here, because it's 0 minus 1 minus 2 versus fold R 0, 1, 2, which will give us a different result, right? And the reason is this one again, it's going to be 0 minus 2 just make sure I get this right. Even a simpler example. This one, 0, 1. Oops, sorry. That's not what I wanted to do. Fold L. This is minus 1 versus fold R, which is 1. Okay. So the difference is obviously in the first case you're doing 0 minus 1. In the second one you're doing 1 minus 0. Okay. So in this case, in the case of fold R minus 0, 1, 2, what it's doing is it's going to start with 0, it's going to subtract 2 from it, which will give us minus 2. Alright. And then what it's going to do is it's going to subtract let me see something here. It's going to subtract a minus 1, which will become a plus 1. See? Hold on. 0 minus 1, 2. Minus 2 is 0 minus 2 is going to be minus 2. So fold L is 0 minus 2. Fold R is 2 minus 0. Oh, right. I'm sorry. So in this case, fold R here is actually doing going to be (1 minus 2 minus 0), which is why it's going to be -1, not 1. For some reason, I was thinking that it's going to be -0 minus 2 minus -1. But what I wrote on the fold R for the plus sign, my apologies, this is going to be 1 plus 2 plus 3 plus 4 plus 5 plus 0. Alright. So in the same application is going to end up being the same thing with if we actually apply in the case of 1, 2. In that case, it's going to be fold L. If we do minus 0, 1, 2, you will end up getting 0 minus 1 minus 2. But in this case, if we do fold R, minus 0, 1, 2, it's actually 1 minus 2 minus 0. So it'll start with 2 minus 0, and then it'll do 1 minus 2. Because the left-hand side, the first argument is always going to be applied to the first element, and then the next argument is going to be the right-hand side, which is going to be the rest of the arguments. So that's it for today. I know this has been a light session. I know we were going to go into more details of the folds. But as you can see with folds, I still need to make sure my understanding of some of the fold syntax is correct. So that's what we're going to be covering next week. For folks who are reading the Haskell book, of course, this is going to be chapter 10 in the Haskell book. If folks are reading Learn You a Haskell, folds are covered in chapter 6. And I think it's covered again in chapter 7 when we talk about modules too as well. So, are there questions? I know today was a bit of a short one, but I will cover folds next week, and there'll be a little bit more of a detailed discussion. I hope to see you all there. I'll see you later. Bye.